Bounded by the Olympic Stadium to the south and the Velodrome to the north, the 2012 Olympic Park in Stratford, London is one of Europe's largest construction projects. And the enabling works at the 2.5 square kilometre site are the most comprehensive ever undertaken in the UK, involving the excavation of 2.3 million cubic metres of soil. In this programme, starting with the ODA's Head of Infrastructure, Simon Wright, we learn how some 800,000 cubic metres of soil and 20 million gallons of groundwater has been cleaned in readiness for the 2012 Games.
We needed to get started urgently. This was back in 2007. The site had been secured, the land was available. So the enabling works contracts consisted of demolition. We had 300 so buildings. We needed to take those apart, demolish them, but we needed to do it in a way that would recycle most of the material. In fact, some of the buildings, like 3 or 4 of the buildings, we disassembled, transported and reassembled in other parts of the country. So the buildings were entirely reused, which is, a good thing from a materials handling and a sustainability point of view. We had a river cleanup program, that is to improve the flood defences and to clean up the waterways. And then we also had dealt with a large volume of archaeological excavation. Part of the English heritage approach, of course, on sites such as this is to look at the history and to excavate and to sample and to detail the artifacts that were found. And we found a number of interesting features, Bronze Age axes and Roman bits and pieces, coins and so on. So archaeology was a key component, and then the remediation of the soil itself, the largest component of that contract, and a number of other things like some ecological transportation. So we take animals and for instance newts that were living on site, take them away so they can safely survive and then be brought back when the parks are reopened. So we had a wide range of activity in the enabling works.
On the site we had 2 principal contractors working on the project, split nicely north of the site and south of the site. The programme for those 2 areas is slightly different. The nature of the ground in those 2 areas were different, and it gave us a balance of resources. It meant if we had a problem on one particular site, we could still maintain the programme. So the philosophy of 2 contractors was set from the start. Underneath those 2 principal contractors, called the Tier 1s, there was a set of Tier 2 subcontractors that carried out the specialist techniques, the groundwater cleansing, maybe the soil washing. So these 2 principal contractors were akin to management contractors. They would do some of the works themselves, but they were principally there to coordinate, manage and lead the overall remediation of the site. Some 2 million cubic metres of earth were moved over a period of 2 to 3 years. On the stadium site behind me now, we moved 400,000 cubic metres of soil within 9 months, cleansed, ready for the platform for the stadium. That was the first key milestone on London 2012. Prior to Beijing, they give the ODA the confidence the whole remediation programme was going to be a success. The overall process for remediation starts as follows. We do a desk study, look at all the existing information around the existing Museum of London, records within the local authority, existing site investigations to establish our model of the site. What do we think this site is like? We then go about a trial investigation program. So some 3,000 boreholes were used to sort of confirm our assessment of what the soil model and the groundwater model was like, down to 60 metres depth, but some very thin 3 millimetre size boreholes just to test the soil vapour. So there's 3 principal soil techniques: the soil vapour analysis, the groundwater testing boreholes, and the soil abstraction boreholes, where we take, say, a 60-metre borehole, test it, sample it. I think over 5 million test results came out of this programme, all of which had to go into the design, all of which were needed to convince the planners we had the right approach to cleansing the site.
We had a 3-tiered system, so we had on-site field analytics to be able to receive instantaneous results which would guide the remedial excavations in terms of whether we need to extend, because we're trying to assess this in terms of risk to human health controlled waters. The second tier was an on-site lab facility to test for geotechnical as well as chemical aspects, and that had a more delayed turnaround in terms of 3 days, but again, it further assisted and generated that level of confidence as to whether we continue or progress that excavation or whether we cease. And then we had the final tier, which is a fully accredited testing methodologies, which was then used to verify that the works that we'd undertaken were appropriate and to the satisfaction of the regulatory teams.
The remediation strategy is based upon dealing with material that we excavate in order, we have to change the levels of the park in order to create the landform that we require for the platforms for the future developments, for the venues and so on. In creating that landform, we excavate quite a lot of soil, and that material we test and if necessary then treat. And we've treated it through soil washing, some bioremediation and some other techniques. Focused primarily on making sure we keep the majority of that material on site. So we treat it and we create material that we can reuse. We then deal with, when we get down to the formation level, we will then test that soil, and if necessary we may go on to excavate what we call hotspots. So individual areas that are contaminated at that level, we go down further and excavate and remove that material. But otherwise the formation level is then left as it is, and then we need to add protection layers above that. So at that formation level we will put down a marker layer, this orange fabric that's been talked about in the media and misunderstood, if I might say so. It's merely a marker layer. It does nothing to protect humans. It's merely to tell you that below that layer is potentially hazardous or contaminated material. Above that we put a capping layer, and that's designed as clean material. It's designed to prevent any upward migration, and for instance it would prevent, if you're in a park, from children digging down into the contaminated soil. So its thickness is designed to prevent risk to human health.
So a huge logistical challenge. Many of the areas were still in public ownership. This site was broken down into perhaps 200 land parcels. Some had existing facilities on them. We had to get access in and around working buildings. We had to demolish buildings and then get back in really quickly to carry out the remaining site investigation to allow us to complete the design, obtain planning and progress safely with the works.
The contaminants we found on the site were a mixed bag of what one would expect from sort of industrial dereliction going back several hundred years. They included heavy metals, so lead, arsenic, those sorts of things. Included a lot of oil-based contamination, mainly from sort of leaking tanks. So we had tars and oils and the byproducts of those, and some other sort of chemicals, including things like benzene. So a wide variety of fairly noxious material, things you don't want to leave in the ground, and things that we are required to deal with in order to protect both the groundwater, but also, of course, most importantly, human health.
We had a range of contaminants on the site, both organic and inorganic. So by organic I mean hydrocarbons. So imagine you have a barbecue, that layer of ash afterwards is a result of incomplete combustion, which has resulted in, they're called polyaromatic hydrocarbons. They're the things that we've identified on the site as a result of that. In addition to that, we have volatile organic compounds, these VOCs. So if you imagine a marker pen, the odour that comes off is a volatile aspect of the products used for that marker pen.
We have, as we announced way back 2 or 3 years ago, we have found some radioactivity, some waste. This is, I might add, naturally occurring material. It is very low level radioactive waste, and it occurs from industrial uses that were on this site, particularly, for instance, luminescent paint. So these are very small flecks of paint from the luminizing industry that existed sort of many years ago, and this would have been used for the dials of aircraft in the Second World War, and also trucks. So trucks, and if you remember, watches used to have luminizing paint on them. So it's a very, very low level material. It is exempt from the regulations, and this material, most of the material we found was either buried safely at depth on the site with a covering to prevent groundwater infiltration, or taken off site for safe disposal in licensed tips.
The approach to remediation, how much soil that we clean, how deep we go, is driven by risk assessments. We look at the end use. If a site, a particular parcel of land has got a hard surface, there's a limited risk of a member of the public getting in contact with the ground. Potentially, therefore, we could leave the soil less clean, in want of a better word, or treat it to a lower level than we would if it was a public open space.
Soil washing was the ODA's chief tool when it came to tackling the site's 800,000 cubic metres of contaminated soil. But other treatments are also used. Bioremediation, for example, in which beds of soil are oxygenated to accelerate the breakdown of oily wastes by bugs and other microorganisms already in the earth. Other contaminants were locked in situ using chemical and physical stabilisation technologies. In addition to the soil, more than 20 million gallons of contaminated groundwater was treated using innovative pumping techniques, ammonia-eating microorganisms, and by the injection of oxygenating chemicals, such as potassium permanganate. But let's concentrate on the soil and start with complex sorting, the initial labour-intensive process that preempts soil washing.
There is no better computer than the human body or the human eye. We'd pass all these materials through, people were picking out pieces of metal and plastic out of large conveyor belts, and that was one of the first stages of really getting these smaller fractions of material cleansed, ready to go into soil washing and the like.
In the old days, one would have only had the option to excavate the soil and really to cart it off-site and tip it to landfill. That is not acceptable nowadays. So first of all, we're looking at options that avoid taking material off-site. And by far and away, the largest volume of material was treated by soil washing.
The soil washing is a relatively simple process. The contaminants effectively cling to the sides of the particles, a bit like, let's call it dirt. What we try to do first is segregate the soil by screening. It goes through large screens, griddles you might want to call them, that separate out the large and the small fractions. When we get down to a size of sands and gravels, maybe the size of your thumb down to, let's say, dust, we put that through the soil washing system. The material goes into the hoppers, is mixed with a lot of water. Cyclones are used to separate the material into different sizes, and then it's screened through different levels to come out with different grades of material. Through that washing process, the contaminants are removed and consolidated into the filter cake. The filter cake, let's call it a large mass of gooey muck, for want of a better word, is about 30% of the resultant soil. That is then disposed of off-site. The sands and gravels coming from these soil washing are then used back into the works. If we look at the techniques we use, about 750,000 cubic metres of the soil went through soil washing. About 30,000 cubic metres went through a process of bioremediation, and that's in two sort of phases really. Lightly contaminated soils with things like benzene, we could put through a rotivation system that would allow the volatile compounds just to aerate. The more heavily contaminated organic substances, the oilies, were put into a controlled environment where we mix the air quality, the temperature, with microorganisms that would effectively go and munch into these hydrocarbons, break them down, and after about 6 weeks, the material would be then clean, ready for reuse in the works. We had a number of other techniques we used, chemical stabilisation and physical stabilisation, of about 300,000 cubic metres of material. So that's in addition to the 750,000. Physical stabilisation, quite a lot of the material would come out of the ground very wet. So to get that fit for use, we would try and abstract the water or bind the water into the material. That would be called that geotechnical or engineering stabilisation, making it stronger, fitter for use. The chemical stabilisation uses proprietary products to lock in the materials, bind them together so that even if water passes over the soil, it won't wash it out and move it to another part of the soil model. You know, we call it, they'd be locked in, and as opposed to being transient.
Clearly, technically, we've avoided excavating material where it's been possible to use alternative measures. So one of the things we've done here, and I think a lot has been learnt, is around treating groundwater rather than excavating contaminated soil. So where we could, and it's not everywhere, we've been able to pump groundwater, which is contaminated, and treat it, and then discharge it back into sewer or the river, rather than excavate the soil within which the contaminants sit. So it's much easier and more efficient to pump groundwater than to excavate large volumes of soil. So by that means we've been able to reduce excavation by a very large volume. So pumping and treating groundwater, and in situ injection. So we've used chemicals, naturally occurring materials, oxidation, things. Potassium permanganate, you can inject down boreholes and cause rapid decontamination of products by accelerating the natural oxidation that they would incur. So a lot of techniques have been trialled here using in situ, down borehole techniques, pumping and treating groundwater, as well as very large volumes of soil washing, which we've carried out probably to a greater extent than anywhere before. In order to ensure that the material we've produced is usable back into the project, we then have had to retest it. So we had an on-site laboratory. It's been disbanded now, but we had it for a couple of years. And in that laboratory, we're taking samples of the products from these treatment processes, and we're retesting them to ensure they comply with the regulatory requirements. And only when they pass those tests can you then reuse them back into the works. And of course, the material in the capping layer has to be clean enough, and that's very clean. And that material has had, in most cases, to be imported. We were able to use the soil excavated from the cable tunnels as part of the capping layer, and we've also used soil from the Channel Tunnel rail link, which was on the Westfield shopping centre site, as capping layer as well. But otherwise, we've had to generally import material. But the soil that we've washed and the products from the remediation we've incorporated below the marker layer, but they all have to be tested and validated, and a lot of documentation provided to prove that they are clean enough.
Has it worked? Is interdisciplinary working the way forward? I think you could take the enabling works as a great example of that. You know, civil engineers moving soil, master planners, architects, scientists, all working together 3, 4, 5 years ago now to think ahead, what's this site going to look like in 2012, and making decisions then in the absence of data. Real foresight, real judgment, you know, real innovation.